Welcome to the example on hypothesis test for a mean class size. It says you receive a brochure from a large university, kind of like maybe University of Tennessee or something like that. And the brochure indicates that the mean class size for full-time faculty is fewer than 31 students. You might think that's great. Small class sizes at a large university. You want to test this claim. You randomly select 18 classes taught by full-time faculty and determine the class size of each. The results are given below here. At the 0.01 significance level, can you support the university's claim? You can see the class sizes listed: 34, 26, 28, 33, 32, 37, 28, 25, 29, 26, 28, 37, 30, 31, 25, 29, 31, and 28. So let's see, what are we claiming? It says here, the brochure indicates that the mean class sizes for full-time faculty is fewer than 31 students. We're testing a claim about the mean, and it says fewer than 31 students. So we're going to use mu as our parameter, and then fewer than 31 students means it's less than, so our alternative is mu is less than 31. It does not contain equality, and h sub a is our claim. That means h sub 0 is our complement, meaning mu has to be then greater than or equal to 31. Also, with our null hypothesis, we can assume the underlying claimed mean equals 31 students. Our h sub a, since it's less than, we are going to say that it's a left-tailed test. Our significance level in our problem, you can see here it's at 0.01. Our rejection criteria. Remember, with the p-value method, we're going to reject h sub 0 if our p-value, our probability, is less than or equal to 0.05. Our t-test statistic. We're going to go t-test statistic is going to be our sample mean x bar minus our claimed mean mu all over s divided by square root of n. Now, to look for our sample data. Well, our sample data we don't have for this except the fact that we only know that there's 18 classes surveyed. We don't know what x bar is and we don't know what s is. So we're going to have to use technology to perform that. Let's go to StatCrunch. Entering our data from above into StatCrunch, now we can find our mean and our standard deviation. So we're going to go to under Stat, then we're going to go Summary Stats in columns. Choose our first variable 1 column, and I'm going to highlight the mean, and then go down and also hit Control and then standard deviation. I'm going to hit Compute. So our sample mean is going to be 29.83333, and our standard deviation is going to be 3.666221. Substituting these values into our problem, x bar 29.8333 minus our claimed mean is 31 divided by s, which is 3.666221 divided by square root of, and again it's going to be, the sample size is 18. So I'm going to go ahead and use technology to find the t-test statistic and our p-value. Back to StatCrunch, we're going to go Stat, and then we're going to go Summary Stats. T-Stats. And we're going to go one sample, and then we can do this hypothesis test. We can choose with summary and enter the data that we just collected into that summary, or we can choose with data since we have our column of data already in StatCrunch. I'm going to go ahead and select the column, variable 1, and then the hypothesis test for the mean. I'm going to choose h sub 0 mu equals our claimed mean is 31 students. Our h sub a is going to be mu is, we're going to choose the less than symbol. And then down here it's going to look a little different, but what we're going to do is under optional graphs and tables, I'm going to hit the p-value plot and then hit compute. Again, on my screen, my new screen, I can hit the bottom arrow at the right, the bottom right hand arrow, and I can see our test statistics is going to be negative 1.3501, and our p-value is 0.0973. I'm going to copy that graph onto my paper. So my horizontal scale is -2, -1, 0 being the mean, 1 and 2. And my test statistic is -1.35. Remember, it's t equals -1.35. Shade the area to the left, and that area on the left is my p-value, which we calculated out as 0.0973. So now our decision. Our decision, remember, go back to the rejection criteria. So our decision is of our p-value, 0.0973, is going to be less than or equal to, and I just noticed here, my significance level is not 0.05, it's 0.01. So I'm going to change that here. Is 0.0973 less than 0.01? I'm going to add a couple of zeros to 0.01, and notice it is greater than. So my decision then for this problem is I'm going to fail to reject the null hypothesis. Now our statement. Let's look at our chart. On our chart, the original claim does not contain equality, so we're going to answer no and go down on the flow chart. Do we reject the null hypothesis? Again, we're going to say no because we failed to reject. And so the sample does not provide sufficient evidence to support. Okay, so that's going to be our option here. Does not support, basically. So back to our paper, we can say the sample data that we collected does not provide sufficient evidence to support the claim that, let's see, the mean class size for full-time faculty is fewer than 31 students. There we go. And we would have to say at alpha equals 0.01. Okay. Next, it also says, would the same decision be reached if the significance level was 0.10 instead? So let's look at this. Our p-value, remember, was 0.0973. So we got to compare that 0.0973, and we got to compare it now to 0.10. I'm going to add a couple of zeros. So now we can say that this is less than. So our decision now would be to reject the null hypothesis. So what's going to change in our statement? Well, instead of does not when it's failed to reject, it would say does when it rejects. Say the sample data does provide sufficient evidence to support the claim that the mean class size for full-time faculty is fewer than 31 students at alpha equals 0.10. So that's where the significance level comes in. Sometimes if it's really close, you could be reject and fail to reject, but it does make a difference in the outcome. This one's kind of a tricky situation. It's not in a dire situation. For example, it's not like some medical statistics that we're analyzing where you might want to collect more data to be able to test, or regenerate using like bootstrapping methods and stuff like that. But, the significance level does play an important role in these problems.